Okay, sorry about that. So, leading up into this point, we have been looking at differential calculus by looking at how to find the derivative, given that you've got some sort of power function. So remember, power functions are things like f of x equals x to the power of 7, or f of x equals 1 over x cubed, or f of x equals the cube root of x, or something like that, more sophisticated than that. But what makes a power function? A power function is that it can eventually be expressed as a power of some description. So if you did Maths Extended last year, you might recall why on earth we would do this, why we would find this f dash of x thingy. And that's where I'm going to retread some old ground if you've already been through it. I don't think it hurts to see it again. And if you've never seen it, this is your chance to get on top of it. So the idea really is right in front of you. I'm starting off with this idea of a big idea here. So if we just sort of pair back to why on earth do we do all of this in the first place, we've got this. We start off with some real world data. We've seen through our statistics unit that we could take our real world data, plot it, and say, well, that looks approximately like. And what we've done in statistics is we've said it looks approximately like a linear regression, a straight line. But that's not the only kind of regression you can have. You can have a quadratic, you can have an exponential, blah, 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 blah. So the idea is that scientists or statisticians will take the real world data, they will look at the shape of that real world data, and they will see if they can approximate or fit a function to fit as much of the data as possible. We've seen this already. We've seen that we can do things like work out what the y-intercept is as a result. You could imagine you could find out other information like a data point in the future or a data point in the past potentially, if you've got a function to go with. So big idea number one is that we often want to model some real world data as a function. Now, one of the critical pieces of information about a function, about a model of real world data is that one there, okay? The rate of change. So how the data is changing with, how one set of data is changing with respect to the other set of data. So if you're doing something like distance that's being traveled against time that has taken for that distance to be traveled, which is a mouthful, which is why we just simply say velocity. That's real world data that you can map. You can come up with a function, but what you're really interested in is what's happening what's happening with that velocity as you map it, and that's called acceleration, right? The rate of change of velocity is called acceleration. So being able to work out how the data is changing is really important. That's the big idea. That rate of change is really important. So you need to know that the purpose of differential calculus is to work out what is called the instantaneous rate of change. In other words, how the data is changing according to the other set of data at a particular moment. Okay, instantaneous rate of change. The opposite of instantaneous rate, not opposite, but the complementary idea to instantaneous rate of change is an average rate of change, how things are changing over a longer period, not at an instant, at a single point. Okay, so what I just thought I might show you is how that's the end point, that's the end game, right? The end game is to be able to be sufficiently skilled up to be able to understand and calculate these instantaneous rates of change. Note both of those things, understand and calculate. You've already started along that journey by being able to differentiate a power function. Do you understand it yet? Okay, a couple of people are nodding. Okay, that's fine, but you don't have to yet. This is what we're doing today, is we're building up hopefully a deeper understanding of what's going on. So in order to do that, I need to break it down into a few different ideas. Okay, so these are the stepping stones. So to understand the instantaneous rate of change, we need to be able to compare it to the average rate of change. And to understand what all that means, you need to know what those things signify, what average rate of change means, etc. To compare and make a link between those ideas, we need to have an understanding of limit theory. Okay? Why? I'll unpack that as we go along, but I'm breaking down the ideas so that when I start saying random stuff about limit theory, you're not saying, why are you talking about that? That's nothing to do with what we're about differential calculus. It has everything to do with it because it's an underlying idea that you need to be across. And finally then, to understand about limit theory, we need to explore ideas about convergence. So that's going backwards through the steps there. So I'm going to start with looking at convergence, and then I'm going to develop the ideas through there. So I wasn't going to use my my iPad, but I think I will because it makes sense to have the one platform. But note that I don't have a pen though, so I'll be writing with my finger, which just is not that great. So just keep that in mind. So I'm just going to set that up now. Okay. Okay, so again, please forgive the fact that it's going to be a little bit dodgy the way I'm writing with my finger. Okay, so let's have a look at convergence for a start then. Oops, sorry, I'll just keep it zoomed out. Okay, so we have come across the idea of convergence before. So convergence is a value that a function heads towards without actually quite hitting it, but we can say it converges to that value. So when we look at asymptotes, that's an example of convergence. Okay, so it converges to a particular value. So if I have a function, say for example, one on x minus 1 over x minus 1 plus 3, we can say as x approaches 1, f of x approaches 3. And we normally do that as an asymptote. Okay, because when it gets really, really close to 1, this is getting really, really, really close to 1 over 0, which would be equal to 0. Now, 1 over 0 is not defined, which is why we can't say there is a value at x equals 1. Instead, we talk about what happens as x approaches it. And typically, we say as x approaches it from one side or the other. So if we have a look at Desmos, for example, and I type in that function, yeah, we can see 1, 2, 3, there is a horizontal asymptote. Whoops, wrong way around, Richard. At y equals 3, that the function is heading towards that value from either side of 1, but doesn't actually get there at 1. So at x equals 1, as x approaches 1, we can see the function approaches 3. Okay, so that's the general idea with convergence. We've seen convergence as well with series, for example. So remember how we did geometric series and we did 0.99999 going on forever, and we used geometric series to prove that 0.9 recurring was exactly equal to 1. In other words, we can start considering that if we take things to infinity, things start to go a little bit, not weird, but you need to rethink your relationship with numbers, I suppose. That it doesn't quite make sense on one level, but sorry, I'm back onto Air Sketch. I didn't switch back over. On one level, but in terms of thinking about 0.9 recurring, it's not equal to 1, and yet there's no number between 1 and 0.9 recurring, and therefore they are effectively the same. Not even effectively, they are the same value. It's weird stuff, but nevertheless, it's because you have to stretch your brain to not to compensate, to take into account infinity, effectively. Okay, infinitely. Either in this case, there is an infinitesimal gap between 0.9 recurring and 1, to the extent that that gap is unmeasurable, and therefore there is no difference between 0.9 recurring and 1. So this is all convergence stuff. And importantly here, for what we're going to do next, I want to point out that this idea that if I take the limit as n approaches infinity, where n is the number of decimal places, if I stop n at any given point along the 0.9 recurring, then I just have a number that's really close to 1. But as n approaches infinity, the value of 0.9 recurring goes to 1. And so for all intents and purposes, 0.9 recurring is the same as 1. It is the same as 1. Now, the reason why this is an important point is because later on, I'm going to show how we can apply the same limit theory to a rate of change to describe why a particular rate of change is exactly equal to a certain value, because it's going to approach that value. Okay, that'll make sense as we go along. Any questions? This is all big head stuff at the moment. So let's have a look at one more. Oh, no, I've just done that one. That's okay. I was going to look at one more example. But what I'll do is I might just take the notation I've got in slide 1 there and just formalize it a bit. So we can say the limit as x approaches, what was it in this case? 1 of 1 on x minus 1 plus 3 is equal to 3. So the notation there is that this tells me that I'm taking the value of x to a certain value, and we're looking at what happens to the function as it approaches that value. That's what this notation means. So it's the limit, kind of like, if I switch over to the other screen for a second, this is like the limit. The asymptote is like the limit, and we're saying the limit as x approaches 1 from either side will make the function approach 3. Okay, so that's what that means. So we use the word lim, short for limit. We put the value that the variable is approaching underneath it, and on the right-hand side, we write the equation, and we can see that it will approach 3. Okay, that's a little bit of we've looked at limits before in geometric series, so that's a bit of a refresher before I head over to talking about the next concept, which is average rates of change. Okay, any questions? Okay, so in terms of building blocks, we're kind of saying we need to think about what instantaneous rate of change looks like. And the building blocks for instantaneous rate of change is limits and average rate of change. Okay, so both of those ideas feed into a concept of instantaneous rate of change. So we've just looked at limits. Hopefully you sort of get a sense of why limits are important. And now we're going to have a look at average rates of change, or Chang as I've got there. There we go, average rates of change. Alrighty, so to look at average rates of change, I want to first talk about what a rate of change is in general. Anyone got a word for me? What does rate of change mean, Ansel? It is just the gradient. You're absolutely spot on. The gradient, if you remember, I was going to write on the whiteboard. I've got to get out of that habit. The gradient, if you remember, the gradient is just rise over run. Okay, you remember that? That's the basic definition of a gradient of a function. So it's rise over run. So another way of saying it is change in y, that's the rise, over the change in x. Now, often when we talk about the change in a value, we often use the notation of delta. It doesn't, please don't get confused with delta, the discriminant of a function in a quadratic. So we instead write delta y over delta x. Change in y over change in x. Yep. I'll explain as we go along. Yep. So right now, I'll chuck in a word because you're thinking ahead. So delta is often used to describe a big change. Okay, so a big change in y over a big change in x. Okay, so change in y over change in x. And so the idea that we've got a change in one variable with respect to another variable is basically what a rate of change is. You think of your rates of change. It's usually meters per second or liters per what? Liters per meter or something like that. They're always 1 unit per another unit, right? So that's what a rate of change is. One variable is changing with respect to another. Typically, of course, our common rates like meters per second or kilograms per centimeter or something like that are usually per 1 unit. So when we have a really simple linear function, like when you look at these notes later, it's not going to make any sense at all, like 3x plus 2, then we typically say, then, oh, well, that means 3 units in the y direction per 1 unit in the x direction, don't we? Okay, in other words, it goes up by 3 units for every 1 unit across. Okay, so if 3x plus 2 looks like this, that means that for 1 unit across, it's gone up 3. Oh, that's I know the graph is just dodgy, but it kind of means that 3 units up for 1 unit across. Is that okay? That's what it means. Sometimes it's a bit more explicit. So if you had something like y equals 2/3 x plus c, plus 2, that would mean 2 units in the y direction and 3 units in the x direction. And that would be like 3 and 2 units that way. Is that okay? So note that rate is almost always, no, the rate is always the change in y over the change in x for any function. I'm just focusing on linear functions because they're the most easiest to see at the moment. Okay. So here is a linear. So anyone got any questions about that first of all? So the main thing to take away right now is that a rate of change is effectively the gradient of a function. Okay, let's have a look at one. I'm going to give you a moment or two. Which one do I want? Yes, that one. Oh, go away. What I want is for you to work out the gradient of this. Let me give you the context. This is a graph which relates length of time taken versus distance traveled to get to Launceston. You can see that Launceston is 200 and I think 10 kilometers away from Hobart. That's approximately right. you can see that it took me 3 hours to get to Launceston. Can you please work out the speed that I travelled to get to Launceston? In other words, the speed is kilometres per hour. It's a rate. Therefore, you need to work out what? Gradient. If you can't make a start, that's fine. In a couple of minutes, I'll unpack it for you. But I'm hoping everyone here can work out the gradient of a linear function. Jeremy, did you want to ask a question to clarify? Am I not saying something clearly for you? Change in, remember, rate is change in y over change in x. Just do it. Yeah. It's not meant to be hard. Sorry? There's no trick to this. You got an answer, Zoe? You look a bit zoned out. You okay? If I splash water over your face, that help? Until I find out it's vodka and then we're in real trouble. I'm just saying you're not dizzy, you're drunk. That's what I'm trying to say. Oh, that's going on the recording. Maybe that should. For the recording, Zoe is not drunk. I was joking. You okay? You sure you're okay? Yeah. Okay. You got an answer? I think so. Have you got an answer? Okay. Sophie, have you got an answer?
I have the magic skill, Richard.
What, of distracting Sophie?
Yeah.
Just knowing speed. We've got Zoe drinking up here. You're taking speed. What else is going on? Ansel's happy, so that's ecstasy. This is just a drug-ridden class, this is. Well, if you need to leave, you just leave.
I made a full-on script and then yes.
Okay, Rosie, what did you get? Okay, nicely put. So the gradient of this particular function is 70. And then to put it into context, because it is kilometres travelled per time taken, it's 70 kilometres per hour. Now, Archie said something before, which I'd like him to repeat for the benefit of the crowd. Go for it. What did you say about that speed? No, before then. You said it with a bit of a disparaging sound to your voice when you said it. No, that's slow.
Oh, that's slow.
Yeah, that's a bit too. And he's right. 70 kilometres per hour would frustrate any driver on the road if you're going up to Launceston at that speed. But,
Unless you're learner.
beg your pardon?
Unless you're learner.
Your max is 80. That's true. It's still slower than a learner, isn't it? And you know what? If you're a learner and one of your learner tasks is to drive to Launceston, that's a very tedious thing to do because it's pretty easy. It's a pretty easy drive, though. Is my point. This is the point. If you think about it, 70 kilometres per hour is in fact not the speed that I was doing, because 70 kilometres per hour implies that when I turned on my engine, I instantaneously went to 70 kilometres per hour and I stayed at that until I said, stop, done, right? So in other words, it doesn't actually represent any particular speed. It instead represents the average speed. It's the average speed, okay? You can see from this, and you know what? This graph is just a little bit of a makeup a bit, but you can see that from home, I started to speed up to a certain speed, probably in town where it was 50 kilometres per hour. Once I got out of town, I was able to speed up, and this is along the Midlands Highway or whatever, where the speed was a bit fast. Anyone want to work out what this point here is? Yay, Campbelltown. Stop for a hot chocolate for half an hour. Yep, for half an hour. You can see it's from 2 to 2.5, where my speed was 0. But yeah, whatever it happens to be. I stopped for half an hour for a rest and to have a wee, and then I got back in the car, and then I travelled to Launceston again. So you can see that although my average rate of change was 70 kilometres per hour, my speed at any given moment was, at any given moment was only 70 kilometres per hour here and here. Well, you could if you wanted to. Can someone please work out the speed I was travelling? I can't remember. Maybe I hit some sort of other town as well, because I slowed down a bit here. Between 1.5 and 2, here is my speed here. Actually, let's make it more interesting. Let's go for the fastest. Between here and here, I was going faster. See if you can work out how fast I was going between those 2 points. I'll tell you what the points are to help you. This one here, so my speed hike was at 0.5, so half an hour after I left home. And then I kept that constant speed up until 1.5. My speed when I started accelerating was 20 kilometers an hour. And then, sorry, not 20 kilometers an hour. I had traveled 20 kilometers at that point. And then here it's 100 and looks like 135 by the looks of it. 135. So between 20 kilometers and 135, I was going at that new speed. 135? 20. I'm just reading from the graph. Oh, actually, no, I'm wrong. I'm wrong. It says 25. It is, but they don't tend to ping you at 115. It's not like 110 you're fine and 111 up. Sorry, ticket. There's usually about a depending on the state, right? Some states have a 10% error. Oh, okay. In some places in Australia, they say there's a 5 kilometre per 5 kilometre per hour allowance. Others say a 10% allowance, and that's to why do you think they do that? This has nothing to do with math. Nope. Nope. But that's true. It's really simple because very few people are driving precision instruments, and maybe the speedo is a little bit slow or fast, and maybe the speed gun that they're using to track you on is a little bit slow or fast. So they give you a bit of an allowance. All right. I think the best thing is to not speed, but that's just me. Yeah, and you know what? I just find that to be entirely ethical and full of integrity. I'm going to do it from now on. Kind of legendary. Okay, can we move back? I knew this would happen. This is my fault. Guys, rein it through. Rein it back. Rein it back. Jeremy, zip it. Ambrosia, ignore him. Okay, let's refocus. So even this graph here is a bit of a fudge, right? So if you calculated it properly according to the values that it was supposed to be, that's from 25 to 135. It's 110 kilometers per hour, which is the limit. But we know that's not going to be true. Not really, because I'm not going to. I mean, I've still got a change of speed that's gone from one speed here, bang, to this speed here. Now I'll do this on the whiteboard because it's not worth switching over. But really, it's probably going to be more like a whole bunch of exponential graphs kind of thing, isn't it, in terms of the speed? So it's just an approximation. But the point being that an average rate of change just looks at two gross, a starting point and an end point, and just tells you what's happening in between on average. And we know from our statistics unit that on average, that an average never has to actually appear in the data set. An average doesn't have to appear in the data set. And you can see that what's actually happening is across here. So in order to calculate the speed, say on the Midlands Highway, for example, I actually had to just take a snapshot of a smaller set of data. And if I did that, I got something which was closer to the speed I was doing at the time. In truth, it was probably a little bit more variable than that. Maybe I started to accelerate above 110, as Ambrosia pointed out, to overtake someone, but then drop my speed back a little bit, going around the corners and stuff. So it's still an average in and of itself, okay? But it gets you a bit of a sense of what's going on here. So we have average rate of change, and then if we can look at smaller snapshots of the data, we can get what's actually happening at the time. In truth, there's only really one way that I would know what speed I was traveling at any given point. This graph's not good enough. What would that be? Not even more precise than that. Think practical. Don't think this graph on the board. Don't even think about graphing. Look at the speedo. Yeah, look at the speedometer. So when I'm traveling along and I want to know how fast I'm doing, I don't tend to draw a graph. I tend to simply look at the speedo and say, oh, I'm doing 75 kilometers per hour. Better drop it down because it is in a school zone. No, I wouldn't do that. You know what I mean? You have to look at the speedometer, obviously. And when you look at the speedometer, you get an instantaneous rate of change. Now, this is where the problem lies. When I'm traveling on the Midlands Highway and I see that I am traveling at 110 kilometers per hour, or let's be honest, let's say it's 112 kilometers per hour. I will need to slow down, but right now, sorry, Rosie, she's upset now that I've been speeding 2 kilometers per hour over the speed limit. But you know what? I'm going to learn to manage Rosie's disappointment. 112, yeah. So when I am looking at that, I am looking at a single point. This is the bit that we need to get our heads around. It's a single point of data, correct? A single point of data. Now, this is the thing. If I've got a single point of data, why aren't I still? Why aren't I standing still? Because for rise over run, change in y over change in x, I need to have a change in y and a change in x. I don't have that. I've only got a single point, and yet I'm confident that I'm actually traveling fast when I'm doing 112 kilometers per hour. Okay, so at a single point, we have instantaneous rate of change, as in at that instant. That's what it means. I've got to learn how to spell. It's not true. Oh, now I've got rate of choice. What does that mean? Rate of change. Okay, at a single point, I have an instantaneous rate of change. And what I need to be able to do, other than obviously look at my speedo and see what I'm traveling at and all that kind of stuff, what I need to be able to do is be able to evaluate what an instantaneous rate of change would be. Because the truth is, it doesn't fit our classic model of rate of change. There is no change in y over change of x because I haven't changed anything because I'm at a single point. Does that make sense? So what we need to do and what differential calculus allows us to do is to bridge the gap between average rates of change, which is simple, change in y over change in x, to an instantaneous rate of change, which is why, Ansel, we tend to use a lowercase delta to refer to it. So it's lowercase delta y over lowercase delta x. And this means, yep, small change in y with respect, which you normally write as WRT, to a small change in x. Now, this is the thing. Remember how I talked about limit theory and stuff? So if I make that the size of that change, I can't see this on the video, but I'm squinting my eyes and putting my fingers up near my eyes and going closer and closer towards each other. If I make that small change smaller and smaller and smaller until it all but disappears and then keep on going smaller, i.e. if I look at that small change at an infinitesimal level, then we can say that's the rate of change at that point. Get it? So it's an average rate of change at an infinitely small scale. Now, unless you're Greek, people don't tend to be used to writing in Greek letters, and so this just gets grossly written as dy by dx. So the d is just the anglicized Greek letter delta, lowercase delta. So dy by dx, remember, it means small change in y over small change in x. Shh, you're allowing yourself to be distracted again. Okay, dy by dx. And this is called, by the way, yep. Yeah, definitely go. Do you want someone to take you with you to make sure you get there? Yep. Thanks, Jeremy. We can put you in a wheelie chair. Just for fun. No, not for you, just for fun. Yeah. Okay. So, Zoe, when you're up for it, this will be on Google Classroom. Yeah. Take care. Now, it's called Leibniz notation. So, Rosie, just a link for you. F dash of x and dy by dx is the same concept. One notation comes from f of x, and the other notation, this one, Leibniz notation, comes from y equals. It's just a different starting point with how you're describing your function. Okay, but I use it to start with purely because dy by dx is exactly what it says on the tin. It's a small change in y over a small change in x. I'll pause there for a moment and ask if there are any questions. Yep. That's what we're going to do next. Good question. For the video, I'll just say Ambrosia just asked. You basically asked how that links to what we've been doing. Yeah. So that's the final link, I suppose, in a sense. Yep. Yeah. So if you start with y if you start with y you go dy by dx. Yep. Go f dash of x. No, it's dash. Don't say one. Say dash. If you want to make the connection between the two, if you want to use dy by dx, but you've started off with f of x, just simply state this, and you should do for communication, that f of x equal y, then dy by dx equals blah, 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 blah. Just as simple as that. I love the communication questions answer, so thank you for that. Okay, so let's answer Ambrosia's question in stages, but we're up to step 4 now. So let's just revisit where we've got so far. What we're doing is we're trying to figure out about instantaneous rate of change. Okay, so if I go back to my Word document, in order to work out instantaneous rate of change, we've covered limit theory and the idea of convergence. We're now going to come back to this idea. We've now got this far. To understand the instantaneous rate of change, we need to be able to compare it to average rate of change. Thinking about that statement, does that make sense now where we're headed? Yeah, okay, so that's success. If you can see, I can see there's a link between average and instantaneous, and I understand what rate of change is. That is success for you, okay? So moving back to our air sketch document, the next thing is to look at is the instantaneous rate of change again. So what I'm going to do, Hope this is the right one. Yep, this will be good. What we're going to do in a practical sense is apply the same sense of average rate of change to a function that we're all familiar with. This is just what? Answer, what's that graph? Be more precise. You're right. Be more precise. It's the simplest one. Rosie, help him out. All quadratics are parabolas. No. It's all right. It's f of x equals x squared. This is just the basic graph. No, there's lots of perfect square functions, but like f of x equals x plus 2 all squared would also be a perfect. Why am I arguing? Hang on, I'll start again. Yes, Ansel, you're king of the world. And that's recorded as well, so we know it to be true. Everything you hear recorded is true. Everything else is fake news. Okay, so what we have here is two specific points on our graph. This is our regular f of x equals x squared graph. You can see up to the right there, I have 3 squared equals 9. Hence, we've got 3, 9. And we've got 1, 1, because 1 squared equals 1, right? So it's just, I'm going to write this on the whiteboard, but I'm just writing down that this is f of x equals, in fact, I might just keep to my y notation, y equals x squared. Okay, very quickly, would you agree that that green line would represent the average rate of change between those 2 points? I would. Yeah, is everyone okay with that? No tricks there. Can you work out what that rate of change would be? I can turn off the lights if it helps. Okay, I'm going to switch over to Air Sketch now so we can just talk about it. So, look how I'm using delta y over delta x, because it's a big change in y over a big change in x. We would have 9 minus 1 over 3 minus 1, which is 8 over 2, which is 4. So the average gradient between those 2 points is equal to 4. Okay? Now, at no single point on that parabola is the gradient actually 4. There might be a point there, actually, probably in the middle or something. But the simple point being is that it certainly is not representative of every single point between those two. But it is an average between those. How could we make it a more accurate gradient? What did we do with our trip to Launceston, for example? What was I doing when I made it all squiggly, Jeremy? Focusing on you?
So you were making more than one gradient based on the class. You're making a
Right. Yeah. I broke down the trip, didn't I, into those more than one bit. Good. I can do a similar sort of thing here. Now, what I'm going to do is I'm going to keep the bottom point the same because it's nice and easy, 1, 1. And if you have a look at what I do with the 0.39, have a look at the green line itself. Can you see that it's actually getting closer? So if I get to 2, it's actually really, the gap between the green line and the red line is a lot less. And so you'd think that the green line there would be a better representation of what's happening on that part of the curve. No, Tara? True. So I'm certainly not extrapolating as far as 9, say, for the function. But in terms of being between 1 and 2, would you agree that the line, I mean, have a look at I'm not too sure if I can just do it. Have a look at the gap between here and here. So if I go, say, 2, 4, So the point that I'm sort of aiming for, as I move this value up here, slide it back up again, would you kind of agree that the green line, even between these 2 points, moved further away? So all I'm suggesting is that when we get to that point, that line is closer to the curve. But Tara's also right in that I've just moved it closer to each other, and if you actually zoom up, it's still quite far away, isn't it? But it's better. So if I have the values between 2, 4 and 1, 1, what's the gradient now? We have change in y over change in x. And we have 4 minus 2 over 2 minus 1. So that's 2 over 1, which is equal to 2. Now, obviously, that doesn't say anything other than we've got a change in gradient, but that gradient reflects a smaller interval, effectively. Okay? It's a smaller interval. But we would say that it's probably closer. Yeah. Yeah. That would make more sense to me as well. So what was it? Sorry, it was, what was it? 3 minus 1. What were the values again? 4 minus 1, thank you. But the point being is the gradient's changed, and it probably more accurately reflects what's happening in the graph at that point, the function at that point. Well, what we can do is we can continue to move, oops, sorry, wrong spot. We can continue to move these 2 points closer to each other until they're almost on top of each other like so. I feel like I'm losing the audience. We've only got a few minutes left to go. I was trying to get through it all because I'm not confident that I'm going to be here tomorrow because I'm not feeling very well. But I will stop the video there because there's no point talking to if I've only got the attention of about 3 of you. So I'll upload this to Google